Time is not the steady, universal clock we believe it to be. Your entire perception of reality is about to be challenged as we explore 30 mind-bending facts about the nature of time itself. By the end of this journey, you will understand the universe's strangest secrets, from how black holes trap time to the real possibility of traveling into the future. We will uncover why you age slower on a mountaintop, and if the past and future are already written. What single idea about time feels the most mysterious to you right now? Our everyday experience tells us time ticks by at the same steady rate for everyone, everywhere. But this comforting rhythm is an illusion. The true nature of time is far more fluid and bizarre, a reality first unlocked by Albert Einstein. His theory of relativity shattered the idea of a single universal clock. Time is not absolute. It is relative, meaning it can stretch and shrink, speeding up or slowing down based on two key factors: your speed and the local strength of gravity. This is not science fiction. It is a fundamental property of our universe, verified by countless experiments. One of the most famous ways to picture this is the twin paradox. Imagine a pair of identical twins. One remains on Earth, living a normal life. The other boards a spacecraft and embarks on a journey through the cosmos at a significant fraction of the speed of light. From the Earth twins' perspective, time on the rocket appears to crawl. Years pass on Earth, while only months or weeks might pass for the traveling twin. When the space-faring sibling finally returns home, they would step out of their ship, biologically younger than their brother or sister who stayed behind. This is not just a thought experiment. We see this effect in action every single day with the Global Positioning System. The satellites in the GPS network are moving at high speeds relative to the Earth's surface, and are also located further away from our planet's gravitational pull. Both of these factors cause time for the satellites to run slightly faster than time for us on the ground. If the sophisticated computers on these satellites did not constantly correct for this tiny time warp, the entire system would become useless within minutes, making your navigation app wrong by several miles. The very technology we rely on to find a coffee shop proves that time is not what we think it is. That tiny, almost imperceptible drift in time is not a theoretical glitch. It is a measurable, physical reality, proven with some of the most accurate timekeeping devices ever created. Scientists have placed ultra-precise atomic clocks aboard high-speed jets. After the aircraft flew around the world, they landed and compared the clock that traveled with one that stayed firmly on the ground. The clock from the jet was ever so slightly behind. It had experienced less time. This same principle applies on a much larger stage, the International Space Station. Hurtling through orbit at thousands of miles per hour, the astronauts and every clock aboard are living just a fraction of a second in the future compared to us. The effect becomes even more dramatic when we look at our planet's silent sentinels, the Global Positioning System satellites. These machines orbit high above Earth, where our planet's gravitational grip is measurably weaker. This combination of high speed and lower gravity creates a fascinating tug-of-war on time itself. The speed of the satellites tries to slow their clocks down, but the weaker gravity tries to speed them up. And in this cosmic contest, gravity wins. The clocks on board GPS satellites actually run faster than our clocks on the ground, gaining about 38 microseconds every single day. That might seem insignificant, a mere blink in the grand scheme of a day. But in the world of precision navigation, where light travels nearly 300 meters in just 1 microsecond, an uncorrected error would compound catastrophically. Your phone's map would be wrong by several kilometers after just a few hours, rendering the entire system useless. So the engineers who designed the system had to pre-adjust the satellite clocks, building Einstein's relativity directly into their circuitry. Every time you use your phone to find a route, you are relying on a century-old revelation about the fluidity of time. This is not an abstract equation in a textbook. It is the invisible force that gets you to your destination. But this strange stretching of time is only half the story. A far deeper mystery awaits, one that asks a question so fundamental we rarely even think to ask it. Why does time only move forward? We never see a shattered glass spontaneously reassemble. We never see a splash of milk unmix from a cup of coffee. Our lives are a one-way street from the past, through the present, and into the future. This directionality is known as the arrow of time, and its origin is one of the most profound puzzles in all of science. The most compelling answer lies not in the laws of motion, but in a concept from thermodynamics called entropy. At its heart, entropy is simply a measure of disorder or randomness in a system. The second law of thermodynamics states a simple, inexorable rule. The total entropy of the entire universe is always increasing. It never decreases. The universe is on a relentless march from order to disorder. Think of a brand new deck of cards, all perfectly sorted by suit and number. That is a state of low entropy. Now, shuffle that deck just once. The order is broken and the entropy has increased. You could shuffle that deck for 1 billion years and it would never, ever return to its original, perfectly ordered state by chance alone. That is the arrow of time in action. The entire cosmos began in an unimaginably ordered state of incredibly low entropy, the moment of the Big Bang. From that single, hot, dense point, the universe has been expanding and evolving, its disorder constantly growing. This ever-increasing entropy is what gives us our past, our present, and our future. It is the reason we remember yesterday but not tomorrow. It is the physical law that writes the story of our lives in one direction only, forward. This relentless march from order to disorder gives our lives a clear direction, but it also hides a deeper truth about the universe's structure. We are all accustomed to navigating the world in 3 dimensions, moving through length, width, and height. Yet to truly understand our place in the cosmos, you need to add one more coordinate to your mental map: time. In the grand scheme of the universe, specifying your location is only half the story. You must also specify your moment. Think of it this way: your home has a fixed street address, but that address is meaningless unless you also state when you are there. Is it last Tuesday or is it next year? The physicist Hermann Minkowski, building on Einstein's work, realized that space and time are not separate entities. They are woven together into a single, inseparable fabric called space-time. In this 4-dimensional continuum, every single event, from the birth of a star to you reading these words right now, is a unique point defined by its 3 spatial coordinates and its 1 time coordinate. This has a profound implication for your own existence. Your life is not just a series of disconnected snapshots. From the perspective of the universe, your entire life, from birth to this very moment and beyond, forms a continuous thread weaving through the space-time fabric. Physicists call this your world line, a single, unbroken path that traces your journey through all 4 dimensions. This unified view of space-time is not just a philosophical idea. It is the very key to understanding gravity itself. Einstein's general theory of relativity revealed that gravity is not a mysterious force pulling objects together across empty space. Instead, mass and energy cause the space-time fabric itself to curve and warp. Imagine placing a heavy bowling ball in the center of a taut rubber sheet. The sheet stretches and curves downward. Now, if you roll a marble near the bowling ball, it will spiral inward, not because a force is pulling it, but because it is simply following the curved path, the geometry of the sheet. Planets orbiting a star are doing the very same thing. The Sun's immense mass creates a deep well in the space-time around it, and Earth follows the curved contour of that well, an effect we perceive as the force of gravity. You are not being pulled toward the ground, you are sliding down the gentle slope of space-time curved by the Earth's mass. Your world line is simply following the path of least resistance through a bent universe. This curvature of space-time does more than just guide the paths of planets. It directly warps the very fabric of time. Gravity does not just pull on matter, it pulls on time itself. The stronger the gravitational field you are in, the slower time passes for you. This phenomenon is known as gravitational time dilation. Right now, as you sit or stand, the force of Earth's gravity is ever so slightly slowing your clock compared to someone in a higher altitude. If you were at the foot of a massive skyscraper, time would tick slower for you than for a person standing on the rooftop. The difference is incredibly small, just nanoseconds over a lifetime, but it is real and measurable with today's technology. This effect is a direct consequence of living in the curved geometry of spacetime. The closer you are to a source of mass, the deeper you are submerged in the gravitational well, and the more stretched the dimension of time becomes. While these differences are tiny on Earth, they become astronomical when you approach the most extreme objects in the cosmos. Near a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons, gravity is immense. Time there would crawl at a fraction of the rate we experience, but this is merely a prelude to the ultimate time warp, a black hole. Imagine observing a clock as it fell toward a black hole's event horizon, the point of no return. From your safe vantage point far away, you would witness a bizarre sight. The clock's ticks would appear to slow down, stretching further and further apart. As it approached the event horizon, the ticks would become infinitely long. From your perspective, time at the very edge of the black hole would appear to stop completely. The clock would seem to freeze, its final tick never arriving as the object is red-shifted into oblivion. For the clock itself, of course, time would pass normally, and it would cross the horizon according to its own timetable. This stark difference in experience highlights a core truth. There is no single, universal now. What you see as frozen in time, another observer might see as having already happened. So if time can freeze at the edge of a black hole, what does that tell us about the journey of our astronaut twin from the beginning of our story? The twin paradox presents a puzzle that seems to defy logic. If all motion is relative, then from the rocket twin's perspective, it is the Earth that speeds away and returns. So why is only one twin younger? The answer lies in a critical detail we have not yet explored. The situation is not symmetrical. The twin on Earth remains in a single, unchanging reference frame, a state of constant motion, but the astronaut twin does not. To embark on the journey, to turn around and to finally return home, the rocket must accelerate. It must fire its engines to change speed and direction. This acceleration is the key that breaks the symmetry. It is an absolute experience that the traveling twin feels physically, a force pinning them to their seat, which the Earthbound twin does not share. This period of acceleration is what solidifies the difference in their experienced time. The astronauts' path through the four-dimensional fabric of spacetime is genuinely shorter. Their world line, the thread tracing their entire journey, has less length in time than the thread of their sibling who stayed home. This is not a trick of perception. It is a geometric fact about the universe. The traveling twin does not just feel younger, they have objectively lived through less time. We see this same principle at work in our most powerful scientific instruments. In particle accelerators, scientists observe unstable particles like muons. When these particles are stationary, they decay into other particles in mere microseconds. But when they are hurled at nearly the speed of light around the giant ring, their internal clocks slow down dramatically. From our perspective in the laboratory, their lifespan stretches out. They travel much farther before they decay, simply because time for them is passing more slowly. The twin paradox is no longer a paradox. It is a confirmed prediction of a universe where time is a flexible dimension, and where acceleration leaves an indelible mark on reality itself. This ultimate speed limit of the cosmos has a mind-bending consequence for the particles that travel at that very velocity. For a photon, a single particle of light, the universe is a profoundly different place. From the instant it bursts forth from a distant star until the moment it strikes your retina, no time passes for the photon at all. Its entire existence, a journey that might span billions of years from our earthly perspective, is experienced as a single, timeless event. The photon does not age. It does not experience a beginning, a middle, or an end. It is, in the truest sense, ageless. This is the full, staggering effect of time dilation taken to its logical extreme. As an object approaches the speed of light, its internal clock slows down relative to a stationary observer. At the speed of light itself, this slowing becomes absolute. Time stops. The mathematical equations of relativity tell us that for a photon, the distance between its origin and its destination contracts to zero. The entire universe is squeezed into a single point, and the trip across that unimaginable void is instantaneous. Now, let us extend this thought to a hypothetical human traveler. If you could build a spacecraft that moved at the true, unimpeded speed of light, the consequences would be even more bizarre than the twin paradox. The moment you engaged the engines, your subjective experience of time would cease. You would press the button to launch, and in that very same instant, you would arrive at your destination, whether it was a neighboring star or a galaxy on the far side of the observable universe. For you, the journey would have no duration. You would not feel a second pass. Meanwhile, back on Earth, millennia could have unfolded. Everyone you ever knew would be long gone, and human civilization might be utterly transformed. You would have traveled into the far future without living through a single moment of it. This is not a flaw in the theory, but a direct prediction of how our universe is structured. The speed of light is not just a limit on velocity. It is a boundary where time itself grinds to a halt for the traveler. This idea that a photon experiences no time leads to one of the most profound and unsettling questions in all of physics. Is the future already written? According to one interpretation of Einstein's own equations, the answer might be a quiet yes. This is the block universe theory, a model of reality that suggests the past, present, and future are not sequential. They all exist at once, fixed forever in a single, four-dimensional structure. Think of this structure not as a timeline, but as a vast, unchanging block. Inside this block, every event that has ever happened or ever will happen has a permanent location. Your first breath as a newborn is not a vanished memory. Your final moment is not an uncertain fate waiting in the shadows. They are both equally real coordinates in this cosmic block. Just as real as the city of Paris and the city of Tokyo are fixed points on a map. In this view, the entire history of the universe is laid out, complete and static. The feeling that time is flowing, that the future is open and the past is gone, is merely a peculiar trick of our human consciousness. We are like a needle on a record player, experiencing one groove at a time and mistaking that single point of contact for the entire song. But the entire symphony, from the first note to the last, is already etched into the vinyl. This is possible because relativity fused space and time into space-time. We accept that spatial dimensions, like length and width, just exist. The block universe theory simply extends that logic to the dimension of time. Your entire life, from beginning to end, is a long, winding path through this four-dimensional landscape, a single thread in the tapestry. This does not mean you lack free will or that your choices are meaningless. It means that your choices and their consequences are permanent parts of the universe's geometry. The theory is philosophically jarring, yet it is a valid and consistent way to interpret the mathematics that govern our cosmos. It forces us to confront a bizarre truth. The relentless, flowing river of time we feel in our bones might be the most convincing illusion of all. This block universe, where all of time simply exists, forces us to confront the ultimate origin of that timeline. Where did the block itself come from? What happened before the Big Bang? The startling answer from modern cosmology is that the question itself might be a trick of language, a grammatical error on a cosmic scale. The words before and after are temporal markers. They only have meaning within the framework of time. Asking what came before the Big Bang is like asking what is north of the North Pole. You can travel north until you reach the pole, but once you are there, the very concept of northward travel loses its meaning. Every direction from that point is south. Similarly, the Big Bang may not represent an explosion in space and time, but the very origin of space and time. There was no before, because there was no time for a before to exist. In the standard model of cosmology, the universe did not emerge into a pre-existing void. Space-time itself, all four dimensions, burst into existence from an infinitely hot, dense point known as a singularity. The first fleeting moments of the cosmos were so extreme that our current laws of physics simply break down. We can project our models back to within a tiny fraction of a second after the beginning, but at time zero, the equations yield nonsense. This does not mean something mystical occurred. It means our understanding is incomplete. To peer into that first picosecond, physicists are developing new theories. Some propose a cyclical model, where our universe is just one in an endless series of big bangs and big crunches, an eternal cosmic heartbeat with no true beginning or end. Others explore the idea of a quantum foam, a seething, probabilistic sea of virtual universes bubbling in and out of existence, with our own being one bubble that inflated into the cosmos we know. These are not proven ideas, but they represent the frontier of human thought, a desperate and brilliant attempt to answer a question that may, in the end, be unanswerable with our current minds. The origin of time remains the greatest mystery, the ultimate horizon beyond which our logic and our language may simply fail. While the origin of time remains a profound mystery, its structure may have a fundamental limit. There is a smallest possible unit of time, a single tick of the universe's most precise clock. This unit is known as the Planck time, a duration so incredibly brief it defies human comprehension. The Planck time is approximately 10 to the power of -43 seconds. To grasp this scale, imagine comparing a single second to the current age of our universe, which is nearly 14 billion years old. Now, take that entire cosmic time span and multiply it by trillions. That vast duration is still shorter than 1 second is when compared to the fleeting blink of a Planck instant. This is not merely a very small number. It represents a fundamental boundary. At scales shorter than the Planck time, our understanding of reality completely shatters. The elegant equations of Einstein's general relativity, which describe the smooth curvature of space-time, collide with the bizarre, probabilistic rules of quantum mechanics. In this sub-Planck realm, the very fabric of space-time is thought to cease being smooth and continuous. Instead, it might become a seething, foamy mess, a granular substance where the concepts of before and after lose all meaning. You cannot have a duration shorter than the Planck time for the same reason you cannot have a temperature lower than absolute zero. It is a boundary built into the geometry of the universe itself. Think of a digital photograph. When you zoom in closely, the beautiful, continuous image breaks down into individual, blocky pixels. The Planck time is the universe's pixel, the smallest meaningful unit in the tapestry of reality. This presents physics with its greatest challenge, the quest for a theory of quantum gravity that can unite the cosmic and the quantum, revealing what truly happens in those first fleeting moments of existence and within the heart of a black hole. The Planck time is not just a theoretical curiosity. It is the final frontier of time itself, a whisper from the quantum void telling us that even time has a fundamental grain. If our universe has a fundamental unit of time, could it also have a structure? Scientists have now discovered a form of matter where time itself takes on a crystalline pattern. These are time crystals, and they defy everything we thought we knew about stable states. Normal matter, when cooled to its lowest possible energy state, settles into a quiet, motionless ground state. A diamond is a perfect example of a space crystal. Its atoms arranged in a rigid, repeating structure in 3 dimensions. But a time crystal is different. Even in its ground state, its atoms are never still. They oscillate back and forth in a persistent, repeating rhythm without any energy input. Think of it as a clock that ticks forever without ever being wound. This is not some theoretical fantasy. The concept was first proposed in 2012, and by 2017, separate teams of researchers had successfully created time crystals in laboratory settings. The secret lies in a phenomenon called time translation symmetry breaking. In simple terms, the stable state of the crystal is not the same at all points in time. Its lowest energy state is one of perpetual motion, a constant, regular change that repeats like the hands of a clock. This does not violate the laws of thermodynamics, because the crystal is not outputting energy or doing work. It is not a perpetual motion machine. Instead, it is a new, non-equilibrium phase of matter, a system that is stable precisely because it is constantly cycling. The implications are staggering. Time crystals could form the bedrock of a new generation of quantum computers, providing an incredibly stable framework for qubits that is protected from environmental noise. But beyond the technology, their very existence forces us to reconsider the fabric of reality. We are accustomed to crystals having order in space. The discovery of a crystal with order in time suggests that time itself may have a hidden architecture, a regularity we are only just beginning to perceive. Your own mind is a master of temporal illusions, warping your sense of time from one moment to the next. During a sudden car crash or a moment of sheer terror, seconds can feel like minutes. Your perception of time grinds to a crawl. This is not a supernatural event, but a biological one. Your brain, flooded with adrenaline, shifts into a state of hyper-awareness. It begins recording memories at an incredible density, capturing every tiny detail, from the glint of shattered glass to the exact sensation of gripping the steering wheel. When you replay this densely packed memory file later, the sheer amount of information makes the event feel like it lasted much longer than it actually did. It is a trick of recollection, a high-definition recording of a moment of crisis that creates the powerful illusion of extended time. The opposite effect grips us as we grow older. The long, endless summers of childhood seem to vanish, replaced by years that blur into an accelerating rush. One popular explanation is the proportional theory. When you are 5 years old, 1 year represents a full 20% of your entire life. That is an enormous chunk of your experience. But when you are 50, 1 year is only 2% of your life. Each new unit of time becomes a progressively smaller fraction of the whole, making it feel psychologically smaller and faster. Another compelling idea points to the power of novelty. Childhood is filled with firsts: your first day of school, your first bicycle, your first love. These novel experiences create rich, vivid memories that act as powerful landmarks in your mind. As we settle into adult routines, fewer of these standout moments are formed. Without new landmarks, the weeks and months blend into a seamless, unmemorable stream, creating the feeling that time is slipping through our fingers. This psychological arrow of time is just as bendable as the physical one governed by gravity and speed. It reveals a profound truth. The time we live and feel is not a single objective river, but a personal stream, shaped as much by the intricate wiring of our own brains as by the immutable laws of the cosmos. This slow-motion echo from the dawn of time reveals the ultimate time machine is already in our possession, a telescope. Peering back into the deep past, astronomers have confirmed that the early universe ran in slow motion, a direct consequence of its frenetic, high-energy youth. When we observe the most distant quasars, the brilliant hearts of ancient galaxies, we are looking over 12 billion years into the past. The light from these celestial beacons has been traveling for most of the universe's history to reach our instruments today. And within that ancient light, scientists discovered a remarkable signature. The flickering and variability of these quasars, which act like the ticks of a cosmic clock, appeared to unfold about 5 times slower than similar processes do in the modern universe. This is not a flaw in the data. It is the universe working exactly as Einstein's relativity demands. In that primordial era, space was unimaginably dense and hot, expanding at a ferocious rate. Matter and energy were packed together, creating a gravitational and kinematic environment where time itself was stretched and dilated on a cosmic scale. From our calm, modern vantage point in a cool, spacious universe, we witness those ancient events as if they were playing back at a reduced speed. This is the most profound time dilation effect ever measured. We are not just theorizing about time's flexibility, we are directly observing its slow, deep breath in the infancy of everything. The universe's own clock was ticking slower, and we can still see its long, drawn-out shadows today. That ultimate boundary of time leads us to the most extreme environment in the cosmos. At the very heart of a black hole lies the singularity. This is a point of infinite density, where all the mass of a collapsed star is crushed into a volume of zero size. Here, our understanding of reality fails completely. The laws of physics as we know them, the very equations that describe gravity and time, cease to have any meaning. The singularity is not just a place of immense gravity. It is a place where the fabric of spacetime itself is torn apart. In this bizarre realm, space and time undergo a profound and terrifying swap. In our everyday world, you can move freely through the 3 dimensions of space, forward or backward, left or right. But you are dragged inexorably forward through time. You have no choice in the matter. Inside a black hole, this relationship inverts. The direction toward the singularity becomes as unavoidable as the future is for us. You cannot stop moving toward it, just as you cannot stop moving toward tomorrow. Meanwhile, what we think of as space, the directions you could use to navigate away, become as fleeting and unreachable as the past. All possible paths, every trajectory, leads directly and inevitably to the center. This is the true nature of the event horizon. It is not a physical wall you could crash into. It is a point of no return in the geometry of the universe, a threshold where the future for any object is redefined in a single, inescapable direction, downward into the pit. From our safe perspective outside, watching an object fall toward a black hole, we witness a ghostly optical illusion. The object appears to slow down, its image reddening and dimming as it approaches the event horizon. To us, it seems to freeze there forever, a permanent monument etched onto the edge of oblivion. But for the astronaut or the clock experiencing the fall, the story is horrifyingly different. Their time continues to pass normally. They would cross the event horizon without any dramatic jolt, unaware of the moment they pass the point of no return. The journey inward, however, would be brief and brutal. The difference in gravity between your head and your feet, a force known as spaghettification, would stretch you into a stream of atoms, all racing toward that final point. The singularity is the end of the line, not just for matter, but for time as a concept. It is the ultimate boundary of our knowledge, a cosmic full stop where the story of physics, for now, simply ends. The terrifying finality of a black hole's singularity seems to slam the door on any hope of time travel, but our universe might offer another, more subtle path. Theoretical physics allows for the existence of wormholes, strange tunnels through the fabric of spacetime itself. Often called Einstein-Rosen bridges, these cosmic shortcuts would connect 2 distant points in the universe, or perhaps even 2 different moments in time. Imagine spacetime as a vast, flat sheet of paper. To get from one edge to the other, you would have to travel the entire long, winding distance across its surface. But if you could fold the paper, bringing one edge right next to the other, a wormhole would be like poking a pencil through the fold, creating an instant bridge. The journey that should have taken billions of years could become a single step. The real magic for time travel, however, comes from the strange properties of time dilation we have already explored. Suppose you could take one mouth or entrance of a stable wormhole and place it aboard a spacecraft. This ship then travels out into the cosmos at a significant fraction of the speed of light. Due to time dilation, clocks near that moving mouth would tick slower than the clocks back home near the stationary mouth. After a year of travel for the moving mouth, decades might have passed for the stationary one. Now, here is the incredible part. The wormhole itself is a tunnel through the folded spacetime, connecting these 2 points instantly. If you were to step into the stationary mouth on Earth, after those decades had passed, you would emerge from the moving mouth at the moment it experienced, which is only 1 year after it left. You would have traveled back in time, arriving decades before you even began your journey from the perspective of everyone back home. This is not science fiction, but a direct, if speculative, consequence of applying the known laws of relativity. The catch, and it is a monumental one, is stability. According to our best models, any naturally forming wormhole would be incredibly unstable. The gravitational forces at play would cause the tunnel to collapse into a singularity in a fraction of a second, long before even a single photon could pass through. To keep it open and traversable, you would need a form of exotic matter that possesses something called negative energy density. This bizarre substance would have to exert a kind of anti-gravity, propping the throat of the wormhole open against its own crushing weight. While tiny amounts of negative energy might be possible through quantum effects, the sheer quantity needed to stabilize a human-sized wormhole is far beyond anything we can conceive of creating. So for now, these bridges through spacetime remain a breathtaking possibility etched into the equations of general relativity, a ghostly blueprint for a machine we have no known way to build. This cosmic map of frozen moments forces us to confront the nature of the present itself. The present moment you feel so deeply, the sharp line between the past and future, is a powerful illusion. In a universe governed by relativity, there is no single, universal now that applies to everyone, everywhere. The reason is simple, yet staggering: it takes time for light to carry information to our eyes. The world you perceive is not the world as it is, but the world as it was. The warm, bright sun you see in the sky is not a live image. It is a delayed broadcast from 8 minutes ago, the time it takes for its light to cross the 93 million miles to Earth. If the sun were to suddenly vanish, you would have 8 minutes of blissful ignorance before its light, and its gravitational pull winked out of existence. We are always looking back in time. The stars in the night sky are not a current map, but a historical archive. The light from the Andromeda Galaxy, our nearest large galactic neighbor, set out on its journey 2.5 million years ago. When you gaze at its faint, smudged light, you are seeing it as it was when early hominids were first walking the Earth. There is no way for you to know what is happening in Andromeda right now, because its present will not become your present for another 2.5 million years. This relativity of simultaneity goes even deeper. Imagine a flash of light occurring exactly halfway between two observers who are standing still relative to each other. They will both see the flash at the same instant and agree it happened simultaneously. But now, picture a third observer moving at a high speed toward one of the stationary observers. From their moving perspective, the light from the flash closer to them will arrive first. They will conclude the events were not simultaneous, that one flash happened before the other. Both perspectives are equally correct. There is no privileged frame of reference to declare one right and the other wrong. This shatters the Newtonian dream of a single, universal clock ticking away for all creation. Your now is not the same as the now for an astronaut on the International Space Station, and it is certainly not the same as the now for a hypothetical being in a distant galaxy. The present is not a point on a cosmic timeline. It is a personal bubble of perception, unique to your location and your state of motion. The shared, universal present we all feel in our bones is the most intimate and convincing lie our senses have ever told us. This strange fluidity in the present moment finds its ultimate expression in the bizarre quantum realm. Here, the very idea of a fixed reality dissolves. A single particle, like an electron, does not have to choose between being a particle or a wave, or between spinning up and spinning down. Until the moment it is observed or measured, it can exist in a blurry combination of all possible states at once. This is quantum superposition, a concept that defies all our everyday logic. But what if this strangeness does not stop with particles? What if it also applies to time itself? One radical interpretation, known as the two-state vector formalism, proposes exactly that. It suggests a quantum system is not defined solely by its past. It is also shaped by its future. In this view, the history of a particle is a two-way street, influenced by both the state it was prepared in and the state it will be measured in later. It is as if the future is reaching backwards, guiding the particle's path. This hints at a form of backward causation, where an effect can precede its cause. The evidence for this temporal weirdness is not just philosophical. It is experimental, demonstrated by one of the most mind-bending tests in all of physics, the delayed choice experiment. Imagine sending a single photon towards a beam splitter, a device that can let it pass through or reflect it, creating two possible paths. In a classic version of this experiment, you can wait until the very last nanosecond, long after the photon has already passed the splitter and is heading toward the detectors, to decide how you will measure it. If you choose to measure which path it took, it will obediently act like a particle, having taken one definite route. But if you choose to set up your experiment to measure its wave-like interference pattern, it will retroactively have taken both paths simultaneously, as if your present-day decision reached back in time and told the photon how to behave moments before. The choice you make now appears to rewrite the particle's past. This is not a flaw in the equipment, it is a fundamental property of the quantum world. At this infinitesimal scale, the clean, one-way arrow of time we experience shatters into a fog of possibility. Cause and effect, the very bedrock of our reality, become blurred. The universe, it seems, does not commit to a single history until it is absolutely forced to. But this quantum blurring of past and future is a luxury of a young, energetic universe. All arrows, even the quantum ones, point toward a single, chilling destination. The ultimate fate of time itself is a state of perfect and permanent stillness known as the heat death. Our cosmos is on a one-way trip from a state of intense order to one of ultimate disorder. And this journey has a definitive end. As the universe continues its relentless expansion, all the energy that currently fuels stars, galaxies, and life itself will become spread thinner and thinner across an ever-growing void. Imagine a single drop of ink in a glass of water. At first, it is a dense, ordered point of color, but slowly it diffuses, spreading out until every single molecule of water is identically, faintly tinted. The entire system reaches a uniform state. No part is any different from any other part. This is the universe's final equilibrium. Every star will eventually exhaust its nuclear fuel and fade to a cold, black cinder. Every black hole, once thought to be eternal, will slowly leak their energy away through Hawking radiation, vanishing in a final whisper. When this process is complete, no pockets of heat or order will remain. The temperature of the entire cosmos will hover just a fraction of a degree above absolute zero, the point where all molecular motion stops. In this vast, dark, and uniform sea, a profound change occurs. The arrow of time, which depends on a difference between states, on a movement from order to disorder, simply vanishes. With no energy gradients to drive change, no processes to mark a sequence of events, the concepts of before and after lose all meaning. There will be no clocks to tick, no minds to perceive, and no events to separate one moment from the next. Time, as a measurable, flowing quantity, will cease to exist. The universe will not end in a violent crunch or a dramatic rip. It will simply and silently run out of stories to tell. entering an eternal, featureless night where the very idea of time is forgotten. The chilling finality of the heat death suggests that time itself can cease. But what if it was never truly there to begin with? A growing number of physicists now argue that time is not a fundamental ingredient of the cosmos. In our quest for a theory of quantum gravity, frameworks like loop quantum gravity and string theory suggest that time, as we experience it, does not exist at the most basic level of reality. It is an emergent phenomenon. Think of temperature. You can feel that a cup of coffee is hot, but the coffee itself does not possess a single unified property called heat. The temperature emerges from the frantic, collective jostling of trillions of individual water molecules. The heat is a useful, large-scale approximation of a deeper, more microscopic reality. In the same way, our flowing, sequential experience of time may be a macroscopic illusion. It emerges from the complex interactions of countless fundamental constituents in a reality that is, at its heart, timeless. At the unimaginably tiny Planck scale, the smooth fabric of spacetime dissolves into a seething foam or a spin network of discrete loops. In this fundamental realm, the equations that describe reality often work perfectly well without any time variable at all. The universe is described not as a history of events unfolding in time, but as a vast, intricate web of relationships. Your perception of moving from one moment to the next is a powerful and persistent illusion, a story your brain tells itself to make sense of this underlying, static network of connections. This does not make your experience any less real. Just as the warmth of the coffee is no less real than the motion of its molecules, but it forces a profound shift in perspective. The true bedrock of existence might be a frozen, timeless geometry of possibility, and the river of time we are all floating on is merely the current we perceive on its surface. Even our most carefully engineered journeys into the void can reveal subtle, unplanned mysteries. The twin Pioneer probes, 10 and 11, were triumphs of human ingenuity, the first spacecraft to travel through the asteroid belt and send back stunning close-ups of Jupiter and Saturn. After their primary missions were complete, they continued their silent cruise into the deep black, becoming humanity's first emissaries to the stars. Yet as they drifted farther and farther from home, tracking their precise positions revealed something peculiar. Both spacecraft were experiencing a tiny but persistent deceleration. They were slowing down just a little bit more than all our calculations of gravity predicted. This minuscule drift, less than a billionth of the gravity we feel on Earth, became known as the Pioneer anomaly. For decades, this tiny whisper from the void captivated and confounded physicists. Here was a discrepancy that our best models of the cosmos could not account for. The deviation was so small it seemed almost trivial. But in the precise language of physics, even the faintest unexpected signal can be a siren's call. It sparked a flood of exotic explanations. Perhaps it was evidence of dark matter subtly tugging at the probes. Maybe it pointed to a flaw in Einstein's theory of gravity itself, requiring a modification on vast interstellar scales. Or, most tantalizingly, could it be a hint of some unknown relationship between gravity and the flow of time, a temporal effect we had never before detected? The mystery persisted for over 30 years, a ghost in the machine of deep space navigation. The ultimate solution, however, was not a rewrite of fundamental physics, but a masterpiece of forensic engineering. A team of researchers embarked on a digital archaeology project, recovering old data and building an incredibly detailed thermal model of the Pioneer spacecraft. They discovered the answer was emanating from the probes themselves. The nuclear power sources generated heat, which the spacecraft radiated away into space to stay cool. This radiation was not perfectly symmetrical. A tiny, anisotropic leakage of infrared photons, essentially light itself, was acting like a faint, braking thruster. The photons carried momentum, and as they pushed off the craft in a slightly unbalanced way, They created the very deceleration that had puzzled scientists for a generation. The case of the pioneer anomaly was closed, yet its legacy is profound. It stands as a powerful lesson in humility. It reminds us that our understanding of the universe is a living, breathing body of knowledge, always subject to revision by the smallest of clues. The next tiny anomaly we detect in a distant spacecraft might not have such a simple explanation. It might be the clue that finally cracks open a deeper secret of spacetime itself. Even the emptiest void in the cosmos is not truly empty. If you could peer into the fabric of space at the smallest possible scale, you would not find a smooth, featureless sheet. Instead, you would witness a chaotic, frothing sea. This is the quantum foam, a seething frenzy of virtual particles that blink into and out of existence in a relentless dance. These particles are not a trick of the light. They are a direct consequence of the Heisenberg uncertainty principle. This foundational rule of quantum mechanics tells us that for impossibly brief moments, energy can be borrowed from nowhere, creating particle and antiparticle pairs that annihilate each other almost instantly, paying back the energy loan before the universe even notices. This endless cycle of creation and destruction is the true nature of a vacuum, a roiling substrate beneath our feet and between the stars. The profound connection to time emerges from this very turbulence. Some of the most intriguing theories in physics propose that these violent, microscopic fluctuations do not just affect matter and energy. They might also cause tiny, random jitters in the flow of time itself. On our human scale, time feels like a smooth, unbroken river. But at the Planck scale, it might be more like a bumpy road, with the rate of time's passage stuttering and jumping due to the foam's chaotic churn. These variations would be unimaginably small, far beyond any current ability to measure. But their theoretical existence forces us to reconsider the very fabric of reality. This leads to an even deeper connection. The energy of this endless particle creation, known as vacuum energy or the cosmological constant, is the very force driving the accelerated expansion of our universe. This intrinsic energy of nothingness is woven into the equations of general relativity, which describe how matter and energy curve spacetime. Since time is an inseparable part of that spacetime fabric, the vacuum's energy is directly coupled to the nature of time itself. The void is not passive. It is an active participant in shaping the temporal structure of our entire cosmos, proving that even nothing is something when you look closely enough. This relativity of simultaneity shatters the comforting idea of a shared cosmic present. Picture two colossal stars reaching the end of their lives, detonating in brilliant supernovas in two distant galaxies. For an astronomer perfectly at rest midway between these two cataclysms, the light from both explosions would arrive at the exact same instant. From their unique frame of reference, the two stellar deaths are unquestionably simultaneous. Now introduce a second observer, this one traveling at an immense speed on a spacecraft headed directly toward one of the supernovas. From their rushing vantage point, the cosmic clockwork looks completely different. The light from the supernova they are approaching will reach them first, simply because they are moving to meet its incoming wavefront. The light from the other, receding supernova will arrive later. This fast-moving observer will swear, with complete physical justification, that one star exploded before the other. So who is correct? Which event truly happened first? The stunning answer is that both observers are right. There is no cosmic judge to declare a universal sequence of events. The order in which spatially separated events occur is not an absolute fact written in the stars. It is a relative truth, dependent entirely on your state of motion. Your personal now is a bubble of perception that travels with you, unique to your path through the cosmos. This is not a philosophical suggestion. It is a mathematical certainty embedded in the structure of spacetime. The universe has no master clock coordinating a single present moment for all of creation. Your now is yours alone, a fleeting and deeply personal coordinate in the vast, silent block of eternity. An ancient Greek thinker named Zeno crafted a puzzle that has echoed through the ages, a paradox that slices a simple journey into an infinite impossibility. To cross a room, you must first reach the halfway point. But before you can reach that point, you must cover half of that half, and before that, half of that half, and so on forever. The path is divided into an endless series of steps, each one requiring a finite moment to complete. If there are an infinite number of these steps, how could you ever possibly begin, let alone finish, your journey? The destination seems logically unreachable, frozen in a maze of infinite divisions. This is Zeno's paradox of the dichotomy, and while it feels like a clever trick, it strikes at the very heart of our understanding of motion and time. Is reality a perfectly smooth, continuous flow where you glide seamlessly from one point to the next? Or is it more like a cosmic film, a series of incredibly rapid, static snapshots that our brain stitches together into the illusion of movement? The mathematical solution arrived centuries later with calculus, which shows that an infinite sum of these ever-shrinking distances and time intervals can indeed add up to a finite, reachable total. You can cross the room because the time needed for each step also shrinks to zero. But the philosophical ghost of Zeno's puzzle never truly vanished. It points directly to the Planck scale, that fundamental limit of time we discussed earlier. If time is truly granular, composed of individual, indivisible Planck time instants, then Zeno might have been onto something profound. Perhaps the universe does operate like a projector, flickering from one frozen frame to the next, at a speed so immense our consciousness cannot perceive the gaps. In this view, your continuous walk across the room is a magnificent illusion, a cosmic stop-motion animation where each new frame is simply the next configuration of the universe. You are not flowing through time, you are being sequentially updated. This idea that motion might be an illusion brings us to another strange implication, one that questions whether the past holds any tangible reality at all. That profound connection between your mind and time raises a question physics alone cannot answer. Why does the universe feel like it is happening to you? Physics masterfully describes how time behaves, but it falls silent on the deepest mystery of all: why we possess a conscious, flowing experience of it. This is often called the hard problem of time. We can chart time's dilation near a black hole and calculate the universe's expansion, but we cannot explain from first principles why you feel a present moment, vividly remember a past, or anxiously anticipate a future. Some neuroscientists propose that this stream of consciousness is not a passive recording. It is an active construction, a narrative woven by your brain in a continuous loop of integrating sensory data, updating memories, and making constant predictions about what will happen next. Your brain is not a camera capturing reality. It is a master storyteller, stitching together the most plausible version of events to create the seamless movie of your life. This process is so efficient that you perceive a smooth, unbroken timeline, even though the underlying neural mechanisms might be a series of discrete cycles of prediction and correction. Without this intricate biological machinery, would time still flow? Or is the feeling of passage, the relentless march from one moment to the next, a beautiful and necessary illusion generated by consciousness itself? This bridges the ultimate gap between the objective clockwork of the cosmos and your intimate, subjective reality. It suggests that time, as you know and live it, is not merely a feature of the universe out there. It is a co-creation, a dance between the physical laws that govern space-time and the unique, perceiving mind that gives those laws meaning. The river of time may flow through the cosmos, but it only becomes a story inside of you. Our reach into the cosmos is creating a cage of our own making. High above our heads, in the seemingly infinite blackness of low Earth orbit, a silent crisis is unfolding. Millions of pieces of space junk, from dead satellites to flecks of old paint, are whipping around the planet at over 17,000 miles per hour. This is not just litter, it is a ticking time bomb. Scientists call the worst-case scenario the Kessler syndrome, a catastrophic chain reaction where a single collision between two objects generates thousands of new fragments. Each new piece becomes a bullet, increasing the probability of further collisions, which in turn create even more debris. This cascade could eventually reach a critical tipping point, surrounding our planet in an impenetrable shell of shrapnel. Launching anything through this field, whether a new satellite or a crewed mission to Mars, would become impossibly dangerous. The skies would literally close. This is more than an engineering problem. It is a profound failure of temporal responsibility. The satellites we rely on for weather forecasting, global communications, and navigation represent our present needs. But the debris they become, and the cascade they might trigger, is a poison pill for the future. Every piece of junk we abandon in orbit today is a decision we are making for our children and grandchildren, a decision to potentially lock them out of the stars for generations. We are imposing a time penalty on our own species, stealing the open frontier of space from future humanity because of the convenience of our present. This orbital graveyard is a stark, physical monument to how our short-sighted use of time in one era can literally rob time from another. This stark reality transforms every dream of interstellar travel into a profound emotional calculation. Reaching for the stars means accepting a one-way ticket into the future, leaving your entire world behind. Imagine a dedicated crew boarding a vessel called the Starchild, bound for a promising exoplanet 100 light-years away. Their ship is a marvel of engineering, capable of sustaining life at 99% of the speed of light. For the crew, the journey is manageable. Due to the intense time dilation at such velocities, their internal clocks slow to a crawl. The trip to the star system and back might feel like only 20 years of their lives. They would grow older, certainly, but they would experience the voyage as a long but finite mission. They would share meals, conduct experiments, and watch as the stars ahead blue shifted, and the stars behind red shifted in their viewports. Yet the moment their ship turns around to begin the journey home, they are committing to a far greater exile than mere distance. While 20 years passed for them, over 2 centuries have unfolded on Earth. The planet they left is gone, replaced by a new world. The political landscapes, the technologies, the very culture they called home would be as alien to them as another species. Their families, their friends, everyone they ever loved would have lived their full lives and died generations ago. The explorers would return as living fossils, the most profound time travelers in human history, arriving in a future built by the grandchildren of their memories. This is the true cost of the stars, a price paid not in fuel, but in time itself. It means that the first humans to travel between stars will be volunteers for the ultimate solitude, cutting the anchor to their own era to bring back knowledge for a humanity they will never truly know again. That powerful, mysterious signal from the void forces us to confront the immense loneliness of our cosmic timeline. In 1977, a radio telescope known as the Big Ear was silently listening to the heavens when it recorded something extraordinary. A burst of radio waves so intense and perfectly structured that the astronomer who discovered it, Jerry Amon, circled the data printout and simply wrote, "Wow." This was not random static. It was a narrowband signal, precisely at the frequency that hydrogen, the most common element in the universe, emits naturally. It was as if someone had taken the faint whisper of space and turned it into a focused, artificial shout. The signal lasted for 72 seconds, rising and falling in intensity exactly as you would expect from a celestial source passing through the telescope's fixed field of view, and then it vanished. We have never heard anything like it since, despite decades of searching that same patch of sky. The WOW signal remains one of the greatest unsolved mysteries in astronomy. Its true nature is a profound puzzle wrapped in the constraints of deep time. It could have been a natural, one-in-a-billion astrophysical event, a freak emission from a passing comet or a distant star that we simply cannot replicate. But the more tantalizing possibility is that it was a deliberate broadcast, a single, fleeting message from an intelligent civilization. If that is the case, then the temporal implications are staggering. The signal originated from a region in the constellation Sagittarius, potentially hundreds or even thousands of light years away. This means the civilization that sent it, if it existed, did so when human history was in its infancy, or even before humans walked the Earth. Their entire species could have risen, built a galactic beacon, flourished, and vanished into extinction during the millennia it took their single hello to reach us. We received a message from a ghost, a whisper from a graveyard. Our frantic search for a reply is like shouting into a canyon, hoping the person who called out a century ago is still there to hear your answer. The wow signal is a perfect, heartbreaking example of the temporal isolation imposed by the cosmos. It is a single, brilliant flash in the dark, reminding us that any conversation between stars will be less a dialogue and more a series of monologues separated by eons. Even the age of the universe, a number that feels so absolute, is now a subject of debate among cosmologists. We know the cosmos is roughly 13.8 billion years old, but how did we arrive at that specific figure? The answer lies in measuring the universe's expansion, a value known as the Hubble-constant. Imagine every galaxy is a dot on the surface of a balloon. As you inflate it, every dot moves away from every other dot. The Hubble constant is simply the rate of that stretching for a given distance. By carefully measuring how fast other galaxies are receding from us, and then running that cosmic film backward in time, astronomers can calculate when all that matter and energy was compressed into a single point, the moment of the Big Bang. This method established our foundational cosmic calendar. Yet, the plot has recently thickened. Our tools for measuring this expansion have become exquisitely precise, and they are now telling two slightly different stories. One method uses the cosmic microwave background, the faint afterglow of the Big Bang, as a pristine snapshot of the infant universe. Another method uses pulsating stars called Cepheid variables and cataclysmic supernovas as cosmic yardsticks to measure distances in our more local, modern universe. These two incredibly sophisticated techniques should converge on the same number for the Hubble constant, but they stubbornly refuse. They are off by just a little, but in the world of precision cosmology, a little is everything. This discrepancy is known as the Hubble tension, and it is not just a minor accounting error. It is a whisper from the cosmos that our standard model of the universe might be incomplete. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant but changing over time. Maybe the early universe had properties we have not yet accounted for, a strange ingredient that slightly altered its initial expansion rate. This tension means the most fundamental clock we have, the age of time itself, might need a subtle recalibration. The universe may be a few 100 million years younger or older than we thought. A mere blink in cosmic terms, but a revelation that proves our quest to pin down time is a story still being written. This fine-tuning of time's very stability forces a deeper question. Why does our universe possess such a precise set of rules in the first place? The fundamental constants, like the strength of gravity or the mass of an electron, seem to be dialed to impossibly specific values. If any one of them were even slightly different, the entire cosmic project would have failed. A stronger gravitational constant, and the universe would have collapsed back on itself in a swift big crunch before the first stars could form. A weaker force binding atomic nuclei, and no elements beyond hydrogen would exist. There would be no carbon, no oxygen, and no chemistry complex enough for life. In such a failed universe, time might be a fleeting blink, or not a coherent dimension at all. So why does our cosmos have this golden ticket? The anthropic principle provides a startlingly simple, almost tautological answer. We can only ask this question in a universe that permits our existence. The fact that we are here to observe time, to measure it and wonder at its flow, means we must necessarily be in one of the rare, viable universes where time is stable and long-lasting enough for observers to evolve. Our perception of a steady, flowing time is not a universal truth, but a profound selection effect. Imagine a vast, silent library containing every possible book. Most are gibberish, random strings of letters. A few might form a single coherent sentence, and an even smaller number contain a beautiful, intricate story. We are not random readers who stumbled upon a masterpiece by chance. We are characters inside one of those rare, coherent stories, and we can only exist within its pages. The constants are not fine-tuned for us. We are a consequence of the constants that allow for tuning at all. This means the river of time we navigate, with its predictable currents from past to future, is not the only way a universe could be. It is simply the only way that leads to us. That deep link between consciousness and time finds a startling echo in the physics of information. Every action you take, every thought you form, is fundamentally an act of information processing. This connection runs all the way down to the cosmic scale, where the arrow of time and the nature of information are two sides of the same coin. You can think of the second law of thermodynamics, the relentless increase of entropy, in a powerful new way, as the law of increasing information disorder. A melting ice cube is a perfect example. In its solid, crystalline state, the positions of its water molecules are highly ordered, a low entropy state where you need very little information to describe its structure. But as it melts into a puddle, the molecules spread out into a random, chaotic arrangement. Describing that puddle requires a vast amount of information, a long list of coordinates for every single molecule. The universe's march toward higher entropy is a march toward greater informational chaos. This principle even applies to the digital world. When you permanently erase a file from your computer's hard drive, you are not just making it disappear. You are increasing the entropy of the system. Before deletion, the magnetic bits on the drive were carefully arranged to represent your document, a state of high order. Erasing them randomizes those bits, scattering their information into an irretrievable, disordered state and releasing a tiny amount of heat into the environment. The act of forgetting, it turns out, has a physical cost. This led visionary physicists like John Archibald Wheeler to a radical proposal. What if information is not just something we process about reality? What if it is reality? He called this idea it from bit, suggesting that every particle, every force, every facet of the cosmos might ultimately be made of information. The physical world, the it, emerges from binary answers to yes or no questions, the bits. In this breathtaking view, what we perceive as the flow of time could simply be the universe processing its own inherent information. Time is the sequence in which these cosmic computations are performed, the relentless updating of the universe's state from one moment to the next. The river of time is not a flow of some ethereal substance, but the processing of quantum information on the grandest scale imaginable. Your entire life, from your first memory to this very instant, could be a unique and intricate computation being run on the ultimate cosmic computer. Perhaps the final destination of time is not a silent, frozen end, but a grand cosmic reset. This brings us to the 30th and final mind-bending fact, the possibility of a cyclic universe. What if the heat death we discussed is not a permanent finale, but merely the closing act of a single cosmic cycle, soon to be followed by a brand new beginning? The cyclic model of the universe proposes exactly this, an endless, rhythmic dance of creation and destruction. In this grand vision, our entire cosmos, from the first flash of the Big Bang to the final dispersal of its last black hole, is just one iteration in an infinite series. The universe expands from a hot, dense state, evolves over trillions of years, and then, instead of fading into nothingness, it contracts. All matter and energy are pulled back together in a cataclysmic big crunch. Some theories suggest this collapse does not end in a singularity, but triggers a rebound, a great big bounce that instantly fuels the next Big Bang, birthing a fresh universe from the ashes of the old. In this model, time itself is infinite and cyclical, a loop with no true beginning and no absolute end. Each new cycle could be a complete reset, potentially starting with different fundamental constants or physical laws. The universe we inhabit, with its perfectly tuned parameters for life, might be just one fortunate roll of the cosmic dice in an endless sequence of universes. While our current evidence, like the observed acceleration of expansion, strongly favors a one-shot Big Bang leading to a permanent heat death, cyclic theories persist at the frontier of cosmology. They offer a profoundly poetic alternative to a finite timeline, a vision where time is perpetually reborn, an eternal phoenix rising from its own ashes across cosmic epochs beyond number. It is a final, humbling thought. The river of time may not flow into a silent ocean, but instead curve back upon itself in a magnificent, unbreakable circle. And there you have it, 30 mind-shattering facts about time that prove our universe is far stranger than we can imagine. From the personal time warps within our own brains to the cosmic time freeze at the edge of black holes, we have seen that time is the most familiar yet most mysterious dimension. It is the invisible river that shapes our reality, our consciousness, and the ultimate fate of everything we will ever know. So the next time you glance at a clock, remember this: you are not just watching seconds tick by. You are witnessing the profound, bendable, and beautiful fabric of spacetime itself. Which of these facts bent your mind the most? Let me know in the comments below. And do not forget to subscribe for more journeys to the edge of reality.